In this section, we're going to talk about directional derivatives and the concept of a gradient. So let's begin with a definition. Let's begin with a function of two variables. So let f of x comma y be a function. And let the vector u be given in component form as the cosine of some angle theta I plus the sine of some angle theta j. So you have a function of two variables and you have some vector that you've gone ahead and parameterized using the angle theta. Here, note that if you take the magnitude of this vector, you're going to have cosine squared of theta plus sine squared of theta underneath the square root, which gives us a value of 1. So here, this is not just a vector, but a unit vector. So let u equal this be a unit vector. Then, the directional derivative of the function f in the direction of the vector u is given as follows. First of all, the notation d sub u, so the directional derivative in the direction of the vector u of the function f of x comma y. So here this is an operator. It's like saying d dx or integral, right? Here you're saying we're taking the derivative in the direction of the vector u of the function f of x. That's going to be given by the limit as t approaches 0 of f of x plus t cosine of theta, comma y plus t sine of theta, minus f of x comma y all over t, assuming this limit exists. So let's actually go and say that, provided the limit exists. Provided that the limit exists. Okay. So what does this say? Well, it defines a derivative in an arbitrary direction. Okay, but can we have a bit more of an explanation on that? Well, let's go ahead and try to expand on this with some illustrations. All right, so let's draw a coordinate system. As always, we have a right-handed coordinate system, so we'll call this x, y, and z. Let's have some function of two variables. Okay, well that's z equals f of x comma y. So I'll have some domain down here and the function up here somewhere. So let's just say something like this. So remember, your x comma y, you have some region on the xy plane that serves as the domain of this function, and then z equals f of xy. Oh, well then that's this surface up here, this sort of dome shape over the domain. All right. Okay, so we have some angle right here, theta. Okay, well, when we say theta, what we mean is you have some vector. Note, this is a vector in the plane. It doesn't have a third dimension. So this vector u is somewhere on the plane. So let's go ahead and draw it. Remember, a vector can have any starting point. So for the sake of convenience, we're going to start it at the origin here. So, all right, so let's say that's our vector u. All right, well then theta is just the angle from the positive half of the x-axis going counterclockwise till we get to the vector u. Now, the same angle that you would have in trigonometry. Okay, so we have some vector. It's in the plane, so it's down here somewhere. And wherever it is, we can measure an angle from the positive half of the x-axis going counterclockwise until we get to that vector u. Now, imagine you're creating a vertical plane from here. So take this vector and then make a plane that has this as the base. So it would extend up this way, and then out this way, and then down this way. Okay, so imagine you have that plane. Okay, well that plane is coming straight up, and it's going to cross through this surface. All right, so where does it cross? Oh, well, if you take this straight, flat plane and just slice right through this, you're going to end up with some curve, something that looks like that. So this is a curve C. All right. So let me go ahead and say all that. So theta, that's the angle between the positive x-axis and some vector u. Notice u is a vector in the plane. And then c is going to be just the curve of intersection between the function, between the surface z equals f of x comma y and the plane extended vertically from u. Okay. Now here, this surface doesn't have to just be above the x-axis. It could be below it, but our illustration would still show this plane would cut through the surface somewhere. All right, so here's your curve C. All right, now consider a line that's going to cross through the origin on the xy plane. It's going to stay on the xy plane, and it's parallel to u. So here, this is a vector, but now imagine you just have a line. So of course the line extends forever in both directions. And we'll call this line L. And so L is a line on the plane that is parallel to u. Like this. All right, well, we can parameterize this line. Here, L, to parameterize the line, we're going to say, okay, we need a starting point. So it doesn't have to be the origin. It could be, but just any point on the line. So here, L can be written as, we're going to have some collection of points. You're going to have some starting point, x naught, comma, y naught. Oh, but that would just put you at a single point. Now we need to have some way of expressing the rest of the points on that line. Well, notice L has this angle theta between the positive half of the x-axis and L. So we can parameterize it using cosine of theta to give us how far we're going along the x variable, and sine of theta tells us how long we're going along the y variable. So here we can say cosine of theta and sine of theta. So those are being added together. You're starting from this point and you're adding some multiple of cosine of theta. So here we can say plus t cosine of theta, and here we can say plus t sine of theta. And so here we're simply parameterizing this line, starting from some point x naught comma y naught on the line, and then using cosine of theta to tell us how far we're going in the x direction, sine of theta to tell us how far we're going in the y direction. And so here we parameterize it with respect to t. Since theta is some known value, here if theta was equal to pi over 6, okay, well then that would be a constant, and that would be a constant. X naught, y naught, again, that's just a single point, so those would be constant. Here you're parameterizing with respect to t. Okay, so now what? Well, let's say we're trying to find the derivative of the surface along this curve. Because after all, the curve is going along the same direction as this line, right? They're all both on the same plane, so they're going in the same direction. Okay, well, borrowing what we remember from Cal 1, to find the slope of the line that's tangent to the curve, you first start with the slope of the line that's secant to the curve. So we pick 2 points that are near each other, find the slope of the line between them, and then sneak those points closer and closer together. All right, so here, I'm going to say this point right here, that is my x naught comma y naught. So here that could be the same as this starting point for my line L. And then over here, I have some point that's just sort of nearby. Okay, so here's my other point, and again, it's along that line. Since the parameterization we see here gives us all the points along this line, here we could just call this point that right there, x naught plus t cosine of theta, comma, y naught t sine of theta, plus t sine of theta. Okay, well then this height, how tall is this? Well, this would be f of x naught comma y naught, because you would plug in that point into our function to give the height, to give the value of z. Okay, well how tall is this one? Well, same thing, it's f of this stuff right here. So f of x naught plus t cosine theta, comma, y naught plus t sine of theta. Okay. So now to find the slope of that line, you're simply taking the change in the y values over the, or I guess in this case the change in the z values, the change in the height over the change in the base. All right, so then the slope of the tangent of the secant line is, all right, we're going to take the change in your heights. Okay, so that would be f of x naught plus t cosine of theta, comma, y naught plus t sine of theta, minus f of x naught comma y naught, we're subtracting our two heights, divided by, okay, well now we need the distance between these 2 points. Okay, well the distance between those 2 points is, well, we need the distance formula here. Here we know the difference in their x values and the difference in their y values, but the difference between the 2 points is actually going to be using the distance formula. So here, the distance of the 2 points along L, okay, well that's going to be the square root of the sum of the squares of the differences of these two. So here I can take x naught plus t cosine of theta minus x naught quantity squared plus, we'll take the difference in the y values. So y naught plus t sine of theta minus y naught quantity squared. Well, that's going to be the square root of, here these two just subtract away, so those go away. We're left with t cosine of theta, which is being squared. T squared cosine squared of theta. Plus, well, these two go away, and you're left with t squared sine squared of theta. Okay, well, the t squared is a common factor, so let's factor that out. That leaves me sine squared of theta. But by the Pythagorean identity, that's just the number 1. So really, this is just the square root of t squared, which is the absolute value of t. Okay, so the difference in our heights was the difference of these two functions. The difference in our base is just going to be the absolute value of t. Okay, so then that's going to be the slope of our secant line. Okay, but we didn't really want the slope of the secant line. We want the slope of the line that's tangent at this first point. Okay, well then have these two get closer and closer together. Well, how do I get those closer together? Well, by making t smaller and smaller. After all, when t is equal to 0, this would be f of x naught comma y naught, which is exactly this point. So here we want the limit as t approaches 0. So the slope of the line tangent at the desired point, which was, what was the point? X naught comma y naught comma f of x naught comma y naught is the limit as t approaches 0. Now here we're taking the absolute value of t, but notice that by our parameterization this is positive, so here we can ignore the absolute value signs there. So here that's the limit as t approaches 0 of f of x naught plus t cosine of theta, comma y naught plus t sine of theta minus f of x naught comma y naught over t, which is our definition. So this motivates why we wish to use this definition as our definition for a directional derivative, and it also shows what all of these things mean. In particular, it shows where we get this expression from, x plus t cosine of theta and y plus t sine of theta. Here, the only difference being that we had an absolute value of t, whereas here we don't. But here, whichever direction our vector happens to be going in, we can define that as we can define our parameterization with a positive t that way. In other words, if I had my t going this way or this way, if I had my vector going this way or this way, I could rearrange my parameterization to still have a positive value of t. So in any event, my limit works out the same. So this motivates this definition. Now, this definition, just like we had the definition for the derivative in Cal 1 or the partial derivative earlier in this course, is the formal definition. However, it's not usually the way we do it, because thankfully we have theorems that were worked out by people long ago that show us how we can have more computational acuity, more efficiency if we have use of some strategies that come from those theorems. So here, theorem. Let's begin with the function of x and y. So let f of x comma y be a differentiable function. Then the directional derivative in the direction of the vector u of f of x comma y is equal to the first partial of f with respect to x at x comma y times the cosine of the angle theta, where again the angle theta is the same angle theta we saw a moment ago. It's the angle from the positive half of the x-axis to the vector u, plus the first partial with respect to y of x comma y times the sine of theta. So, proof of this. Let's start off with a point, x naught comma y naught. So here's that would be the point in the domain where you want the function's derivative at, right? You want the derivative at x naught comma y naught comma f of x naught comma y naught. So here you're taking this as a fixed point. All right, so now let's go ahead and consider a parameterization of x starting from this point. Okay, well, that will be x naught plus t cosine of theta. We're using the same parameterization that we saw in the definition. And likewise, y would equal to y naught plus t sine of theta. Now let's go ahead and define a function g of t, which is f of x comma y. Or in other words, we're now, instead of considering a function of x and y, we're considering a second function, which is the original function, but entirely in terms of t. Okay? Since f is differentiable, the chain rules apply. Thus, we can apply the chain rules to this, and this will give us g prime at t is equal to f sub x at x naught, oh, well, I guess I'm using x and y here, so x comma y times x prime at t plus f sub y at x comma y times y prime at t. So here we're just using the chain rule that shows us what the derivative of the composition is. Here g is f of, and here your x and y are being replaced by these parameterizations. So g prime is the first partial with respect to x times x prime plus the first partial with respect to y times y prime. But we know what x is, so we can find x prime with respect to t. Okay, so that's going to be f sub x at x comma y. If you take the derivative of this expression with respect to t, that's a constant with respect to t. It's a fixed point. So the derivative would be 0. And the derivative of t cosine of theta, well, again, cosine of theta is constant with respect to t. So really this is just coefficient times t. And the derivative of coefficient times t is just that coefficient. So it'll be cosine of theta plus, and same thing for this one. The derivative will be sine of theta. F sub y at x comma y times the sine of theta. Okay, now note when t equals to 0, this implies that x equals x naught, because if t is equal to 0, that goes away. So you're just left with x equals x naught, and y equals y naught. So that means if I take g prime at 0, that's going to give me f sub x at, instead of x and y, that's x naught and y naught. X naught comma y naught cosine of theta plus f sub y at x naught comma y naught times the sine of theta. Okay, but now by definition, g prime at 0 is equal to the limit. Now remember, this is a function of just a single variable, g of t. We're using the Cal 1 definition of a derivative of a function with a single variable. Here that's going to be the limit as t approaches 0 of g of t minus g of 0 over t. Oh, but that's equal to the limit as t approaches 0 of, well, g of t, that was our f of x comma y. So that's going to be f of x naught plus t cosine theta, comma y naught plus t sine of theta, minus, well, g at 0, that's going to be f at x naught comma y naught over t. Here we're taking the function g at t, and remember, since t is equal to 0 for this computation. We have x naught and y naught taking the place of x and y. So here we're taking this definition of f of x, and we're simply substituting in this x for this expression here, f of x naught plus t cosine theta, comma, y plus t sine of theta, that's replacing our x and our y, minus f of x naught comma y naught. But that right there is identically the directional derivative that we defined before at x naught comma y naught. So this is equal to the directional derivative in the direction of u, of f at, and here you notice that's x naught and y naught, so f at x naught comma y naught. Okay, and so therefore the directional derivative in the direction of u of f at x naught comma y naught is equal to this thing that we started with up here, f sub x at x naught comma y naught cosine of theta plus f sub y at x naught comma y naught sine of theta, which is our conclusion. That's what we wanted to prove. All right, so let's take a look at an example of this. Let's find the directional derivative of the function f of x comma y equals to y over x plus y at the point p equals to 3 comma 0 in the direction of the vector u, which is cosine of negative pi over 6 I plus sine of negative pi over 6 j. All right. Okay, so first of all, the notation, that's going to be the directional derivative in the direction of u of the function y, of the function f of x comma y, but we want it specifically at the point 3 comma 0. So this will be the directional derivative in the direction of u of f at 3 comma 0. All right, well that's going to be the first partial of f with respect to x at 3 comma 0 times the cosine of the angle theta plus f sub y at 3 comma 0 times sine of the angle theta. Okay, well we can find all of these. Let me go and do this off to the side. If I take the partial with respect to x of f at x comma y, that's going to equal to taking the derivative of this with respect to x. Note that y is a constant. So this would be like saying I'm going to take the derivative of a constant times x plus a constant to the negative first power. I have a constant times x plus the constant to the negative first power. Just use the power rule. Take my negative 1, bring it down, subtract 1 from the power. So that'll give us negative the constant, which in this case is a y, over, since you subtracted 1, that's now a negative 2, so we can write that as x plus our constant to the second power. Okay, so that's going to give us our derivative with respect to x, but now we're plugging in 3 for x and 0 for y. Okay, well that's going to be negative of 0 over 3 plus 0 squared times the cosine of the angle theta, which is, we see here, negative pi over 6. If you're not given the angle theta, you can always find that if you have 2i plus 3j, you can always find the angle of the vector u. The tangent of y over x is equal to, sorry, I said that backwards. The tangent of theta is equal to y over x. But in this case, they already give you the angles, so you just go ahead and use them. plus, and then over here we're going to take the derivative with respect to y. Okay, well, with respect to y, this is both the numerator and the denominator have a variable. X is a constant. So to find f sub y at x comma y, we need to use the quotient rule. It's going to be the bottom times the derivative of the top. Okay, well, the derivative of y with respect to y is just 1. Okay, so times 1 minus the top, which is a y, times the derivative of the bottom, again with respect to y. Well, that's derivative of x with respect to y is 0. The derivative of y with respect to y is going to be just 1. So that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and all of that is divided by the square of the bottom. It's just a quotient rule. Okay, well, here the y subtract away, so you're just left with x over x plus y squared. And so here we can go ahead and plug in 3 for x and 0 for y. That'll give us 3 over 3 plus 0 squared times the sine of negative pi over 6. Okay, well, that's 0 times, well, it doesn't really matter what that is. 0 times anything, what's going to give us 0? It's going to be 0 plus. Here, that's 3 squared is 9. 3 over 9, that's 1/3, times the sine of negative pi over 6, which is negative 1/2. So in the end, this gives us negative 1/6 plus 0 is negative 1/6. So the directional derivative in the direction of the vector u, as given here, of this function at the point 3 comma 0 is negative 1/6. Going back to our illustration, although this illustration does not match my picture, it still shows the concept. You have a surface, you have a direction, you want to find the slope of the line tangent to the surface in that direction. You have a surface, that's your f of xy equals y over x plus y. You have a vector that gives you a direction, that's your vector u. And now you want the derivative in that direction. So if you imagine you had a tangent line at a point in that direction, that's going to be the slope of that line, negative 1/6. This brings us to our next definition. Let's define the gradient. Let's begin with a function of two variables. Let z equal to f of x comma y be a function such that the first partials exist, such that f sub x and f sub y exist. Then the gradient, and that's what we're defining here, the gradient of f is denoted by this symbol, f of x comma y equals f sub x at x comma y I plus f sub y at x comma y j. This symbol, you could read this as the gradient of f, because that's what it means. However, if you're looking for a word for it, like this is the letter f. Yes, I know it's a function, but what do I call that symbol? Oh, it's the letter f. This is called del. Now you might say, well, wait a minute. I thought wasn't there another symbol you were calling del? Yeah, that's this symbol. That's the uppercase, that's the lowercase. Del represented the partial derivative, right? Del x, del y, del z. Here, the gradient is directly related to the partials. In fact, it is a vector. Notice, that's a vector. It's got two components here. And it is a vector, each of whose components is one of the partial derivatives. So you take the first partial with respect to x, that's the x component of this vector. This is the y partial derivative with respect to y, so it's the y component of this vector. A couple things to note about this. One, that this is a vector in the plane. So note this is a vector in the plane, not in space. The surface is in space, but the gradient is on the plane. Other things to note about this is a vector, which means that it can be written in it can be written in an alternate notation. So let's see, another note. Del f of x comma y is sometimes written as del f x comma y this way, to make it even more explicit. Yeah, that's a vector. It's also sometimes written, although we won't see that in this book, but it's also sometimes written as the gradient of f of x comma y. All three of these mean the same thing. They're just like many of the concepts in our course, they're advanced enough that they've been visited and revisited in history by different people and have seen different notations. So just keep that in mind. We're going to use this. However, these are equally likely to occur in other circumstances, and they mean the same thing. So before we talk about what this is and what it represents and what we can do with it, let's just take a simple example. Here is the function f of x comma y. That's going to equal to the cosine of x squared plus y squared. All right, I'll ask you to do this because really all it takes is to find the two partials with respect to x and y and then put those as components of a vector. So go ahead and give this a try. Find the gradient of f at x comma y. Here you could plug in a number, 1 comma 5. You can always find the gradient at a particular point, but for now just find the gradient. All right? Go ahead and pause the video, give yourself the time you need, and once you're done, go ahead and unpause and we'll go through it together. All right, so we can find the partials with respect to x and y. The first partial with respect to x. Well, let's see. The derivative of the cosine of something is negative the sine of that something. Oh, but now by the chain rule, I have to take the derivative of the inside here. Okay, well, the derivative of x squared plus y squared with respect to x is basically the derivative of x squared plus a constant, which would be 2x plus 0. To take the partial with respect to y, it's almost exactly the same thing. The derivative of cosine of something is negative the sine of that something. But now the derivative of x squared plus y squared with respect to y, well, that's going to be 2y. So that means that the gradient is going to equal to, the gradient of f at x comma y is going to equal to negative 2x times the sine of x squared plus y squared, I, plus, or I guess I should say minus, right? Plus a negative, that's fine, plus negative 2y sine of x squared plus y squared, j. Keep in mind, since this is a vector, we can always write it in the alternate form as negative 2x sine of x squared plus y squared, comma, negative 2y sine of x squared plus y squared. Either of those would be acceptable. All right, now, the gradient is often used for some computational niceties. It turns out a lot of our theorems that we will see going forward can be made nicer if we consider the gradient as a vector rather than having the components of the gradients considered separately. In other words, it's easier to consider the two partial derivatives together as the components of a vector than it is to consider them separately. So this is first seen with the following theorem. First of all, let's have f be a differentiable function of two variables. let f of x comma y be a differentiable function. Then the directional derivative in the direction of a vector u of a function f of x comma y is equal to the gradient of f dot u. That's a vector. That's a vector. You can take their dot product. The proof of this is basically trivial. You just have to compute what the dot product of those two are. But actually, I suggest you try this. Go ahead and show that this is equal to this part. It's not a very heavy computation. Go ahead and take these two, take the dot product, and show that that must equal to that. Go ahead and pause the video, give yourself the time you need, and then we'll come back and see what it looks like. All right, starting from this side, that's going to be the gradient of f. Well, that's going to be, I'll write it in this form. I'll write it as f sub x comma f sub y. Okay, that's the gradient of f. Dotted with u. Well, u can be written as the cosine of the angle theta, comma sine of the angle theta. That's just an alternate form of how we originally defined the vector u, cosine theta, comma sine of theta. Okay? But now the way the dot product works is I just take the first component times the first component plus the second component times the second component, which is f sub x at x comma y times the cosine of theta, comma f sub y at x comma y times the sine of theta. Oh, but that is by, oops, wrong page. That is by our previous theorem, an alternate way of writing the directional derivative. So here that's equal to the directional derivative in the direction of u of f at x comma y. So the gradient of f dotted with u is equal to the directional derivative of f in the direction of u. And that's our result. Notice this is still really using the previous theorem. However, this is just a nicer way to write this. It turns out that this operation, the gradient vector, this operation, which gives us the gradient vector, can be used a bunch of different ways as a vector to either summarize or to more easily compute some rather complicated expressions. Here we see it as a dot product. Later on we'll see it as a cross product or as a triple scalar product. And all of those will have some meaning, as we'll see through the following sections. But for now, let's consider an example. This example will look very similar to the one from before, where we were computing the directional derivative. It's just here we'll see it with an alternate notation involving the gradient. So let's see here. Let f of x comma y equal 3x squared minus 2y squared. We want to find the directional derivative. Find the directional derivative in the direction of u of f of x comma y at the point negative 3/4 comma 0 in the direction from negative 3/4 comma 0 to 0 comma 1. Okay, so we're not given a vector directly. Okay, that's fine. We don't have to be given the vector directly. It's enough that we can find it. Okay. So here for the notation, I'll call this the point P, and I'll call this the point Q. All right, so the vector from P to Q, that's simply You're going to take your 0 minus your negative 3/4, right? You always go from the end point to the beginning point. So 0 minus negative 3/4, comma, 1 minus 0. That'll give us 3/4, comma, 1. Okay. Now remember, u is supposed to be a unit vector. Okay. So let's go ahead and find the magnitude of this thing. The magnitude of PQ is equal to the square root of, you're going to take your 3/4 and you're going to square it, plus you're going to take your 1 and you're going to square it. That'll give us 9/16 plus 16/16. That'll give us 25/16. And if I take the square root of 25 over 16, I get 5/4. So that means that the unit vector u, which is PQ, right, we want that direction, but we want it to be a unit vector. So we're going to divide it by its own magnitude. We're going to take 3/4 and divide it by 5/4. That'll give us 3/5. Then we're going to take 1 divided by 5/4, which will give us 4/5. All right, so we found our vector u. It's not always given, but we can find it anyway. Okay, so now we're going to go ahead and find the gradient. If we find f sub x, that's equal to, well, that's just the derivative of this one. This would be constant with respect to x, so the derivative is 0. So this would simply be 2 times 3 will give us 6x. Oh, not f of x, it's f sub x. And here f sub y would equal to, well, the derivative of this would be 0, and the derivative of this would be minus 4y. So that means that our gradient of f at x comma y, that's going to equal to 6x minus 4y. Just like that. So we want to find the directional derivative, which we see is simply the gradient. Oh, sorry. There you go. That's a vector. It's the gradient dotted with u. Okay, so that means that the directional derivative in the direction of u of f of x comma y is equal to, we're going to take the dot product of these two. So that'll be 6x times 3/5. That'll be 18/5 x. And then you're going to take the product of these two. That'll be negative 4y times 4/5. That's negative 16/5 y. Notice that's not a vector anymore. That's a scalar. You've taken a dot product, the product of those, plus the product of those. And finally, we want to find the derivative at that particular point. So the derivative in the direction of u of f at the point negative 3/4 comma 0. You plug in 0 for this one, which makes the whole thing 0. And if you plug in negative 3/4 here, that'll give you, oh, let's see, that's negative 54 over 20, which we can reduce to negative 27 over 10. And there we go. Here's our directional derivative of our function in the direction of the vector from P to Q at the point P. It's going to give us negative 27 over 10. Notice it's not really any different from what we saw before in terms of the interpretation. It still means all the same thing. It's just now you can remember this as the gradient dot u. This will actually be a very convenient thing because a very similar expression will be used to define something else, the gradient of f cross u, and a few other things will be defined with the gradient. So oftentimes it's helpful to remember how to compute the gradient because the gradient times this, times that, times the other, plus this, plus that, plus the other, all have some specific meaning from just that one vector. Okay, now that we've defined the gradient and we've seen some use of it, here we have a theorem which gives us some properties of the gradient. These properties go a long way in explaining one way of visualizing, one way of interpreting what this gradient even is. All right, so theorem. Let's begin with a function of two variables. Let f of x comma y be differentiable at some point. which we'll call x naught comma y naught. Doesn't really matter what that point is, just differentiable at some point. Then the following things are true. If the gradient of f at x naught comma y naught is equal to the 0 vector, because remember the gradient is a vector, so it can't equal the number 0, but if it equals to the 0 vector, then that implies that the directional derivative in the direction of u of f at x naught comma y naught is also equal to 0 for all vectors u. All right. The second thing, the direction of maximum increase of f is given by the gradient of f at x naught comma y naught. The max value, the maximum value of f of the maximum value of the directional derivative of f in the direction of u is given by the magnitude of the gradient at x naught comma y naught. This gives a good visual as to what the gradient is. You want to find out how quickly f is growing? Okay, well tell me what direction you want to take the directional derivative in terms of. Okay, well now, let's say I searched every possible direction, all of them, 360 degrees in every possible direction from that point. I would find that the maximum increase would happen in the direction of the gradient. Number 3. The direction of minimal increase of f is given by negative of the gradient of f of x naught comma y naught. The minimum value of the directional derivative du of f at x naught comma y naught is given by the magnitude of negative the gradient of f of x naught comma y naught. Okay. The proof of the first one's trivial, right? The directional derivative is f dot u. Well, if f is 0, it doesn't matter what u is. F dot u will be 0. So the proof of number 1 is if the gradient of f at x naught comma y naught equals the 0 vector, then f at x naught comma y naught dotted with u is equal to the number 0, right? If you take a 0 vector dotted with anything else, you get the number 0 for all values of u. So that means, remember this, by our previous theorem, this is a way of computing the directional derivative of f in the direction of u. So that means that the directional derivative in the direction of u of f at x naught comma y naught would equal to 0 for all u. Okay. Number 2 is slightly more interesting, and it helps to illuminate what we mean when we talk about the derivative, at least from a physical standpoint, from a physical interpretation. All right, if the gradient of f at x naught comma y naught, let's say it's not equal to 0. Okay? Then we'll call omega. Omega is a Greek letter, but it looks a lot like the letter W. So if you want to say W, that's fine. But I just like saying the word omega, frankly. Let omega be the angle between the vectors, the gradient of f, and the vector u. Well, then the directional derivative in the direction of u of f at x comma y is equal to the gradient of f dot u. Okay, well that's a theorem we just saw a few minutes ago. Okay, well that's going to equal to, now this is going back to chapter 11, right? This is going back to much earlier, where we saw that an alternate way of saying the dot product of two things is to say we're going to take the magnitude of the first one times the magnitude of the second one times the cosine of the angle in between them. All right, this is an alternate definition of the dot product. Okay. But remember, u is a unit vector, so its magnitude is 1. So here we can just write this as the magnitude of delta f times the cosine of omega, because after all, this is a unit vector. So if you want, you can say magnitude of gradient of f times 1, but, well, we're probably just better off leaving that off. Okay. Thus, this will be as small as possible when cosine of theta is equal to 0, because that's not changing. The gradient is a vector. Its magnitude does not change. Right? If you have the magnitude of a vector at a particular point, that is what it is. The cosine of the angle omega can change, however. And, well, the biggest this can ever be is, well, cosine of omega is between -1 and 1. Okay, so the biggest this can ever be is when the cosine of omega is equal to +1. Thus, the maximum occurs when cosine of omega is equal to 1, which means omega would equal to 0. Right? If cosine of omega is equal to 1, then omega must equal to 0. Cosine of 0 is equal to 1. Okay, but since omega is the angle between the two vectors, omega is the angle between the gradient of f and u, thus there is no angle between them. So they're going in the same direction. Thus the gradient of f and u occur in the same direction. Oh, okay, so that's what we wanted. The direction of maximal increase of f is given by the gradient of f. Okay. If u and the gradient of f are going in the same direction, that's the maximal increase. Okay, so then the maximal direction is in the direction of gradient of f. Not only that, but if this is equal to 1, also, if cosine of omega is equal to 1, the maximum value is the gradient of f times 1. Oh, sorry, the magnitude of the gradient of f times 1, which is the gradient, of f, which is the other part here. So not only is the direction of maximal increase in this direction, but we know that the amount of maximal increase is the gradient of f's magnitude. And number 3 is the same, except well, here this is replaced with a -1. 3, similar to number 2, except you're going to want the cosine of theta. Since you want the minimum value, okay, well then that should be a -1. So cosine of omega equals -1. And that'll work out to this statement here. This is a nice visual, at least I think. Let's say you have a surface. And as always, my surface is going to be a paraboloid because that's the only one I can reliably draw. But this could be any surface. So here you have a surface. Okay, something like that. All right. Now, let's say we want to compute the gradient at a particular point. All right, well, where is that point? It's right here. Here's your x comma y. Now remember, the gradient is a vector, but that vector is not in space. It's on the plane. So when I draw the gradient, it's going to be some vector down here in the domain of this function of two variables. So this would be the gradient of f. So that's the point, and here's the gradient. Okay, so what is that thing telling me? What it's telling me is, okay, if you're standing at this point on your base, okay, now go ahead and plug that point into your function. Oh, well, that'll give you some height. That'll give you some value of z right up there. Okay, now, where you're standing, there are ways where you can go down. There are ways where you can stay horizontal if you follow the same level curve. There are ways you can go uphill. And even then, there's different directions. I can go this way uphill, this way uphill, this way uphill, this way downhill, this way downhill, this way downhill. There's lots of different directions I could go in. Some of them would have me staying in the same height. Some of them would have me going downhill, and some of them would have me going uphill. Okay, well now, out of all of those, which one has you going uphill the steepest? How do I get uphill the fastest? Let's say the water's rising and I want to get to the top as soon as possible. How do I get to the top as soon as possible? Oh, follow that direction. That's what the gradient is telling you. It's telling you want to go up as fast as possible. Go ahead and follow that direction. If you take this and project it up here, that tells you the direction you need to go in to increase your f of x comma y, your height, as fast as possible. Let's take a look at an example of this. And this might be somewhat of an unexpected example, especially given the illustration we just saw here, which relates directly to this theorem. You might expect a very visual example of, okay, here's a mountain you're climbing, or here's something, and you want to go uphill. And of course, those kind of examples would suffice here. However, let's look at an example that it might not be quite so intuitive that they're connected, which shows some of the versatility of this concept. Example, let's say you are on the surface of a metal plate. Let the surface of a metal plate have temperature, and we're going to say that temperature is in Celsius, in degrees Celsius. T of x comma y equals 50 minus x squared minus 4y squared. All right, so here the illustration is not at all necessary, but just to clear things up in case there's any question. You have a metal plate. Okay. Draw your x, y axis right in the middle here, x and y. Okay. The temperature is going to be given in degrees Celsius depending on where you are. So imagine here's your hot plate and here's your heating element. When you're at 0, 0, That's 50 degrees minus 0 minus 0. Oh, the temperature right here is 50 degrees Celsius. Now, as your x and your y move away from 0, then you're going to have 50 minus some number. Oh, so your temperature is going to get lower. So your heating element is right in the middle. That's the hottest temperature on your plate. So right here it's at 50 degrees. And as you move away from there, it's going to get cooler and cooler. So the outer edges are maybe room temperature, depending on how big the plate is. This is a function of two variables. Here you have z, or I suppose in this case T for temperature, is equal to f of x comma y. That doesn't mean that that third dimension has to be a spatial dimension. That's one of the things that commonly gets away from us when we think about visualizing stuff. We think of 3 dimensions as 3 spatial dimensions. No one ever said our dimensions have to be spatial. Here I have 2 spatial dimensions. My third dimension is temperature. Because after all, dimensions don't have to be spatial dimensions. When we talk about dimensions, all we mean are independent measurements, measurements that are not dependent on each other. So here, how far I move left and right is independent of how far I move up and down. Okay, well, you know what else is independent? How high up or far down I am on this page. So here I have 3 spatial dimensions, length, width, and height. But there are other dimensions, like, for example, temperature, pressure, and time of day. Okay, if I put a dot right there, does that change what time of day it is? No, not at all. Okay, well then time is independent of length and width. And if I put a dot right there, does that change the pressure in the room? I wouldn't think so. So pressure is another dimension, right? So when we talk about dimensions, we often talk about, oh, we live in a 3-dimensional world. No, we live in hundreds of dimensions. On the tip of that pen, I can talk about length, width, height. It's about temperature, pressure, time. I can talk about how far away I am from Rome if I want to. I can talk about any dimension that I care to do. There's inertia, there's electrical charge, or anything else I care to think about. So here we're going to take our 3 dimensions. 2 of them are spatial and 1 is temperature. And that's fine. Because after all, our theorems and our definitions do not necessarily state anywhere that we have to have spatial dimensions. All we state is we have to have some value is a function of 2 variables. Z is equal to f of x, y. Here, if z is temperature, well then so be it. All right, so that's our situation. We're on a metal plate, and here's the heating element, which has a maximum temperature of 50 degrees Celsius. And as you move away from the heating element, things get cooler. Okay. Now, let's say you are a little bug. You're sitting somewhere on this plate. In fact, let's give a specific location. You're sitting right here on this plate, which is the point 2, 1. And let's say you're very, very cold. And for some reason, you need to not be very, very cold, right? So what you want to do is you want to move to where it's warmer. Okay, so you want to do this in the most efficient way possible. That's not a nice visual, right? It's not as nice as, oh, things are higher or lower, but it's still something that can be that can be visualized with not much effort. You're cold, you're sitting right there, and you want to move as quickly as possible toward the heating element. Now you might say, well, obviously you're just going to move straight toward it. Well, not necessarily, because notice right here, as I move along the x-axis, I'm subtracting x squared. But as I move along the y-axis, I'm subtracting 4y squared, which means I'm more quickly cooling off in the y direction than I am in the x direction. So that means that going straight there may not be the most efficient way to do it. I may wish to travel more in one direction or another because I don't care about reaching the heating element. I don't know where the heating element is. I just want to get warmer. I want to go in the direction that it's warmer right now. The somewhat morbid analogy, say you're out on the coast and here's the beach, right? Here are the waves, and here's the sand, and I got to figure there's an umbrella in there. And that's what umbrellas look like, I'm sure. I saw one once in my life. I'm pretty sure that's what it looked like. Okay, so let's say you are right over here. And you're trying to swim to the coast. Well, obviously, you're going to swim directly to the coast. But let's say there's a riptide, and there is an extremely powerful current pulling you out towards sea. all of a sudden swimming straight to the beach is a terrible idea, because no matter how strong you swim, you're not going to overcome that current. So what's the fastest way to get to the beach? It's going this way. Same thing over here. Yeah, this may be where the heating element is, but you don't know where it is. You just want to get as warm as quickly as possible. So what you want to do is you want to travel in the direction that warms you up the fastest. That's what the gradient's going to tell us. Find the direction of most rapid temperature increase and find that temperature increase. All right. And incidentally, let me go ahead and move my point over here. I want one of my coordinates to be negative. So let me just go ahead and move this. Let's go and move it down here. 2, negative 1. It doesn't make a difference in terms of the computation. I just want my numbers to work out a certain way. All right, so let's go ahead and do this. We're going to start off by computing the gradient. The gradient of t, you can say gradient of t of x comma y. The gradient of t is equal to, well, it's a vector where the first component is the derivative with respect to x. Okay, well, these are both constants with respect to x, so the derivatives are 0. Here, that's going to give me a negative 2x as the partial with respect to x. Likewise, the partial with respect to y, these are both constants with respect to y, so their derivative is going to be 0. And so here, the derivative of minus 4y squared with respect to y, take your 2, bring it down, will give you negative 8y. Just like that. Okay. So now, let's go ahead and find the gradient. That's the gradient in general, but now we're going to find the gradient at a specific point. So the gradient of t at 2, negative 1, that's going to be 2 times my x value, negative 8 times my y value. And so that's going to be 4, 8. Just like that. Oh, no, it's not. Here, the partial with respect to x was supposed to be negative 2x. So that should be negative 2 times 2. So there we go. My gradient at that point is going to be negative 4, 8. So here that would be what, I want to go back, I want to go left 4 steps and up by 8. So that would be over here and then way up here somewhere. So my gradient would be going in this direction. Notice that is moving me toward my heating element, but doesn't actually go directly to it. It moves me sort of in that direction. So it's not necessarily going to the highest point, it's not necessarily going to the highest temperature, it's simply at this point, which direction would I walk in to make myself warmer the fastest? The other question is, go ahead and find that temperature increase. Okay, well, we're looking for the temperature increase along the gradient, which, as we saw in our previous theorem, is simply going to be the magnitude of the gradient. So that means that we want the magnitude of of the gradient of t, which is the magnitude of this vector here, negative 4, 8. Oh, I guess I should say the gradient of t at 2, negative 1. Specifically at that point. Here, we're not looking for the gradient of the function t in general. We're looking for it specifically where we have our point. All right, so that's going to be the square root of negative 4 squared plus 8 squared, which is the square root of 16 plus 64, which is the square root of 80. Here I can factor that out a bit. That'll give me root 16 times 5, and I can take the square root of 16. That'll give me 4 root 5. So that means that this will be the direction of most rapid temperature increase. And if I do go in that direction, that's going to be the amount of temperature increase in that direction. That would be 4 root 5. Here our unit is in centimeters, is in degrees Celsius. So this would be 4 root 5 degrees Celsius per unit. If this is in inches, well then it would be that many degrees per inch I move. Or if it's in centimeters, it would be per centimeter moved. Right? And this right here is the direction of most rapid increase. So go that way, and you'll warm up that many degrees for every step you take. Now, one note about this. This is an instantaneous measurement. It changes with each movement, with each, let's say, motion. So here, at this point, the temperature that feels the warmest is if I go this way. Now, once I take one step this way, that may change. The temperature may be this way. And if I take a step that way, well, then the temperature might change. So in reality, you're going to end up doing something like this. If you then modify after every step, you'll do something like this, 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 and eventually end up at the heating element. So this is an instantaneous measurement. That doesn't mean that's always going to be the direction of greatest increase. That means at this point, that's the way that feels like you're getting warmer the fastest. Once you take a step, that may change. And in fact, given that we know where the heating element is, of course, we know it's going to change. But that's not what's being asked here. It's not, give me the most optimal path. It's saying, from this point, which way do I go to get the warmest the fastest? All right, now, in keeping with this kind of interpretation of the gradient, let's go ahead and look at this next theorem. Let's begin with a function of two variables. Let f of x comma y be a differentiable function. Let me say it this way, because otherwise that'll be bad grammar. Let it be okay, that's not bad grammar, it's just bad spelling. Let's try that again. Let f be a function that is differentiable at some point, which we'll call x naught comma y naught. And let's have that the gradient of f at that point is anything other than 0. Then the gradient of f at x naught comma y naught is normal. Remember the word normal? It's kind of like saying perpendicular or orthogonal to a curve or to a surface. We'll see that when we illustrate it here in a moment. Is normal to the level curve through x naught comma y naught. Okay. All right. A quick visual before we see the proof of this. Think back to a previous section where we talked about level curves. And here we're going to take all of the points all of the points x comma y such that z is a constant. So, okay, all right, so where is z equal to 0? Well, over here. Okay, well, where is z equal to 1? Oh, all of these points. Where is z equal to 2? All of these points. Where is z equal to 3? All of these points. Like that. Those are our level curves. All right, now, let's say you have a function f of x comma y. Here are the level curves. Let's say it's differentiable at some point, which we call x comma y. Okay, well, let's say this is the point. So I'll call this the point x comma y. So x naught comma y naught. Okay, what it's saying is that the gradient, assuming it's not the zero vector, that should be the zero vector. Assuming that it's not the zero vector, is going to be normal, is going to be perpendicular to the curve through this point. All right, well, there's the point. There's the curve through the point, the level curve through the point. Imagine a line that's tangent to that curve at that point. It would look something like this. Right, so there's the tangent line. What we're saying is that the gradient is going to be normal to that curve at that point. Another way of saying that is that the line tangent to the curve at that point will be perpendicular to the gradient. So right there, that's going to be the gradient of f at x naught comma y naught. That's perpendicular to the line that's tangent to the curve at that point. All right, so there's the illustration, but why should this be true? I mean, yeah, I guess I can see it here in this one picture, but that doesn't mean it's true in general. All right, so let's go ahead and prove this. Let's begin with f of x comma y. And note that it is a constant for any xy on the level curve through the point x naught comma y naught. Or in other words, okay, here's the curve. Here's the point. Here's the curve. Every point on that curve has the same z value. Well, of course, that's why that curve exists in the first place. It's a level curve. It's the point. It's the collection of all points that have the same z value. Z equals f of x, y. Okay. So now, that means that the directional derivative in the direction of u of f of x naught comma y naught is equal to 0 if u is in the direction of the unit tangent vector. At x naught comma y naught. Okay, so all of the points on this curve are a constant, which means if I'm moving along this curve, the derivative is 0. It's not going up or down, it's 0. Everything's constant. The derivative of a constant is 0. Oh, okay, so then as long as I'm moving in the direction of the curve, well, how do I move in the direction of the curve? Oh, well, you follow the tangent vector, right? You follow this line right here, which is tangent. And if it's tangent, it's telling you, okay, if you move in that direction, you're going to move to the very next point on the curve. Okay, so the directional derivative will be 0 if u is in that direction, moving you along the curve. So that means that the gradient of f at x naught comma y naught dot u is equal to 0. After all, one of our theorems tells us that's one way to compute the directional derivative. You take the dot product of the gradient of the function and the unit vector u. But notice that here we began with the assumption that the gradient of f was not 0, and we know that u is not 0 because it's a unit vector. Okay, so then we have the dot product of two non-zero vectors, which gives me 0. Thus, by definition, what do we call two vectors whose dot product is 0? They're orthogonal. Thus, by definition, the gradient of f at x naught comma y naught is orthogonal to the vector u. Oh, but the vector u is the unit tangent vector. So here, the gradient is orthogonal to the unit tangent vector. So then it's got to be, by definition, that means it's normal to the curve. Now that's what it means to be normal to a curve. It means you are orthogonal to the tangent vector of the curve at the point. So since that's what happens to the gradient of f, therefore the gradient of f at x naught comma y naught is normal to the level curve. That passes through the point x naught comma y naught. And that is our result. All right, so let's take a look at an example of a use of this theorem here. One thing to note about the sections that we have been seeing for the most part, we haven't really been using many of these theorems or definitions for bigger purposes. We've simply been seeing examples that illustrate how the theorem might look, but we haven't really used them for a greater purpose. We haven't really seen, okay, here's what we can do with them. Chapter 13 is largely a section where we build mechanics that are then used in the coming chapters. In chapter 14 and 15, we're going to see a lot of uses for this notation. We're going to have uses for the gradient, we're going to have uses for these level curves, and really just about everything we see in chapter 13. So chapter 13 is sort of gearing us up and giving us the equipment necessary for chapters 14 and 15 to make sense. You start to really have, well, I may have a different definition of the word than you, but you really start to have fun in chapters 14 and especially chapter 15. You start to see things like, well, you start to see theorems with names on them. So far we've seen theorem this, theorem that, this theorem, that theorem. The fun ones are the ones that are important enough to have someone's name on them. Stokes' theorem, Green's theorem, things like that. So here we're going to see a few, we're going to see another theorem, which again is not totally, an example that is not totally a realistic example. It's just a simple example of how the theorem we saw works. But that's what we want right now. We want just to have enough understanding of the basics of the theorem. In the next chapter, they will be combined and applied to some bigger purposes. So for now, the example is simply, let's go and find a vector that's normal to a level curve. Now, why do we care about that vector? Just for the sake of knowing how to find it. In a later section, really in the next chapters, we'll see use of all of the things that we've developed in this chapter. If it wasn't necessary for the next two chapters, it wouldn't be included in this one. All right, so example. Let's go ahead and find the vector that is normal to the curve f of x comma y equals 25 at the point p equals to 3 comma 4. Given a function f of x comma y equals x squared plus y squared. Okay, so first of all, we have a level curve. Here's our function in general, but we don't care about the function in general. We want specifically the level curve where your function is equal to 25. Okay, so my level curve is going to be x squared plus y squared equals 25. It's a circle of radius 5. We don't particularly care about that even. We simply want, given our previous theorem, we want the gradient. So here the gradient of f is equal to, well, the derivative with respect to x is 2x, comma, the derivative with respect to y is 2y. So there's our gradient. And now we want the gradient at a particular point. All right, so that'll be the gradient of f at 3, 4, which would be 2 times 3, 2 times 4, which will give us the vector 6, 8. So that will be the vector that is normal to the curve at that point. And while it's not really necessary for this, a quick illustration will help further confirm the visual interpretation that we saw in the previous theorem. All right, so we're going to take a bunch of level curves. All right, our function is f of x equals x squared plus y squared. So our level curves are all going to be circles. All right, we want the level curve at 0. Well, that's going to be x squared plus y squared equals 0. You want the level curve at 1. Well, that's going to be x squared plus y squared equals to 1. So you would have your level curves would simply be circles, all centered at the origin. So let's see, 1, 2, 3. 4 and 5. Just like that. Okay. So now we want to find the vector that's normal to the curve, to the level curve at 3, 4. Okay, well 3, 4 actually does put us on the 5th ring, right? If you use the Pythagorean theorem, 3 squared plus 4 squared is equal to 25. So that does put you out here on the 5th ring. 3, 4. All right, so now if you found the line that was tangent to the curve, that would be this one. Okay, so now we want to find the vector that's normal to the curve, which again we find is the gradient. At that point will be 6, 8. Okay, well 6, 8, that would have you move, oh, let's see here. That would have you move 6 units to the right and 8 units up. So that would be what? 1, 2, 3, 4, 5, 6, and then up 1, 2, 3, 4, 5, 6, 7, 8. And your vector would go up from here going up that way, which even with my crude drawing, that really does look like that's orthogonal, doesn't it? Like that. Note that it's not going toward the center. Remember, the gradient always goes in the direction of most rapid increase. Notice right here, this is the height of 0. 1, 2, 3, 4, 5. Your f of x and y is increasing going that way, not this way. So here you might have expected it to come to the origin, but no, it goes in the direction of the fastest increase. In this case, it's increasing as you're going away from the origin. So here this confirms a couple of things. One, yes, this gradient is normal, is to the curve, to the level curve. It's orthogonal to the line tangent to the level curve. And it does, quite apparently, move in the direction of the fastest increase. All right. And finally, for this section, all of this that we've talked about can be extended into a greater number of dimensions if we need to. And, well, we will occasionally have the need to. Definition. Let f of x, y, z. Up to now we've only been dealing with functions of 2 variables, but here we can see how it would extend to a function of 3 variables. Let f of x, y, z be a function that is continuous with first order partial derivatives defined. All right, so we know what f sub x, f sub y, and f sub z are. Let u be some vector, and we notice the notation, we're talking about a unit vector. Let u be a I plus b j plus c k be a unit vector. Then the directional derivative of f in the direction of u is, we have a similar notation. It's going to be d sub u, so the directional derivative in the direction of u of f at x comma y comma z. You have a third component. That's going to equal to a times f sub x at x comma y comma z I plus b times f sub y at x comma y comma z j plus c times f sub z at x comma y comma z k. Note this is an extension of the definition that we had for the directional derivative of a single variable, where here we see, well, I guess this wasn't the definition, right? The definition involved a limit. Here was our first theorem that showed us how to conveniently calculate it. It was the first partial times the first component of u plus the second partial times the second component of u, and well, now we have the third partial, the partial with respect to z, times the third component of the vector u. So it's a extension by adding the extra component and extending this into a vector of space. Notice here, this a, b, and c is the unit vector. So if we want to maintain the same notation of the directional derivative as being the gradient of f dot u, then we have to define the gradient as follows. The gradient of f of x comma y comma z is, we're going to use the same notation. We're going to say del f of x comma y comma z is equal to f sub x at x comma y comma z I plus f sub y of x comma y comma z j. This looks like the definition for the gradient that we've had for vectors in the plane. So now we have a third component, f sub z at x comma y comma z k. And now we define this as a vector not on the plane, but as a vector in space. Note all properties here continue to be true. Note all properties of directional derivatives and the gradient of a function of two variables, of a function whose domain is in the plane, extend to those of a function of three variables, f of x, comma y, comma z. In particular, the directional derivative in the direction of u of f of x comma y comma z is equal to the gradient of the function f of x comma y comma z dot u. The gradient of f at x comma y comma z equals to 0 implies that the directional derivative in the direction of u of f at x comma y comma z is equal to, oh sorry, that should be a 0 vector, is equal to the scalar 0 for all u. 3, the max increase of f is in the direction of the gradient with the max value of the directional derivative of f at x comma y comma z equal to the magnitude of the gradient at that point. And finally, number 4, the minimal increase of f is in the direction of negative the gradient of f of x comma y comma z, and the minimal value of the directional derivative of f at x comma y comma z is equal to the magnitude of the gradient at that point. In higher dimensions, you have a slightly different notation with the extra component. Otherwise, everything still works exactly the same. And that brings us to the end of our section. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.